Now for the second part of the talk, I show how the subquantum theory resolves these anomalies. The resolution actually is very simple and physically reasonable. As the subquantum particles separate, they become misaligned due to spurious local interactions or instrumental defects. Imagine an entangled source and two subquantum particles separate. They are correlated only by their common orientation with no quantum channels. As the two beams pass through prisms, mirrors, and are filtered by polarizers, the two beams can get misaligned. Recall I called the product state of two particles a biparticle if they come from the same singlet state. In that case, they must have the same value of their hidden variables, and therefore are correlated from their source. Now the hidden variables theta orients the structure in 3D space. The anomalies arise when spurious effects misalign them. This means that Alice's and Bob's orientation can get out of sync a bit, which gives a small asymmetry between the two. For 0.05 pi radians, we see that the coincidences become separated and shifted, and the marginal shows structure. The total correlation, however, remains close to the quantum result. Now with 0.1 pi radians mismatch, it can be seen that P++ and P-, are similar to experiment. The P+- and P-, coincide quite well, which means there is little misalignment in those arms of the experiment. Clearly, the trends are correct. On the other hand, with a little effort, encouraging agreement is found. Here is an angle range of up to pi/2, and the trends are reproduced. See P++, P-, P++, and P-. Finally, most dramatically, the marginals qualitatively agree with the subquantum results. This data supports the subquantum theory, and as we will see, is experimental evidence for a new state of matter. Let us look at this subquantum theory in more detail. As I mentioned before in blog number 4, I adhere to the statistical interpretation of quantum mechanics, which means that although we might observe single events, we can only calculate the outcome statistically by averaging over many individual particles, that is, over sub-ensembles. In fact, I will show that the filters in the EPR experiments pick out different sub-ensembles of spins, and these sub-ensembles account for the anomalies. The statistical interpretation is the only one that considers that a subquantum theory could complete quantum mechanics. But what are these sub-ensembles composed of? Quantum states are composed of ontic particles. That is, they are dispersion-free and all their attributes are simultaneously elements of physical reality. These particles are governed by the subquantum theory. Just a brief outline, a quantum state is an ensemble of subquantum particles, usually all prepared in a similar way for the experiment. That is, the statistical ensemble interpretation of the wave function. The subquantum particles have a two-dimensional structure, rather than the point particle quantum spin. Isolated subquantum particles display a new state of matter. Entanglement is resolved into product states. Now spin arises from the Dirac equation. The free particle Dirac equation is obtained by linearizing the relativistic energy from which spin emerges as a Lorentz invariant, and therefore an intrinsic property of matter. However, you cannot get the magnetic moment, say for an electron, from the free particle Dirac equation. You have to add a probe. In the second form of the Dirac equation, the scalar and vector potentials for the electromagnetic force are introduced. This means that the basic symmetry of the free particle Dirac equation and the particle in the presence of a probe is different. In the free particle case, the environment is isotropic, while in the presence of a probe, it is anisotropic. The magnetic moment of an electron is only obtained by using a probe, and it successfully gives the correct Landé G factor of 2, This leads to the view of intrinsic angular momentum as a vector quantity carrying angular momentum along a single axis of quantization. It is assumed in quantum mechanics that the intrinsic angular momentum found in the presence of a probe also exists in the absence of a probe. This is the point of divergence between quantum mechanics and the subquantum mechanics, by recognizing that it is not valid to assume that the anisotropic solution is valid for the free particle solution. The vector spin angular momentum determined by the probe does not carry over to the free particle solution because of spontaneous symmetry breaking. The symmetry goes from lower symmetry, a vector field, to a higher symmetry, a scalar, when the probe is removed. This is the reverse of most symmetry breaking that is found in physics. Usually an interaction is turned on due to a potential, and the symmetry is lowered and the degeneracy is lifted. How is this done for a free spin? It is postulated in the subquantum theory that the four-dimensional Dirac spinor space of a spin 1/2 breaks into two non-Hermitian components. This is the basis of the subquantum theory presented here. Quantum mechanics requires spin states to be Hermitian. The individual particles that form the ensembles that make up the wave function do not obey the usual SU2 symmetry. They are non-Hermitian. Now this is a radical departure from quantum mechanics, but in all cases, spin states are manifest as Hermitian. However, the symmetry reduction introduces additional degrees of freedom to the spin, and as symmetry breaking usually does, introduces degeneracy too. I'll break here again, but I will continue with part 3 of the talk by showing how subquantum particles have structure, and how they lead to a new spin state and disentangle the entanglement of quantum mechanics.